Mr. Chairman, on-board guests, ladies and gentlemen, good morning. I am honored and proud to have the opportunity to speak at this meeting. I am the reporter of this report, Wang Qian, from the School of Information Science and Engineering, Yanshan University, Qinhuangdao, Hebei Province, China. The collaborators in this work are my senior brother Li Pengyu and my supervisor, Professor Wang Jinjia. Today, I would like to present my paper, ARCSCNet, an approximate residual convolutional sparse coding network for compressed sensing. I will introduce this work from the following four aspects. The first part is an introduction. In this section, I will focus on the advantages and disadvantages of existing CSMR techniques. As we all know, CSMR technology is designed to reconstruct MR images from undersampled k-space data, which is much less than Nyquist sampling. Existing CSMR methods include model-based methods and deep learning-based methods. Model-based CSMR methods explore sparse regularization in specific transformation domains or dictionary-based subspecies. However, in terms of performance, the basic CSMR methods with traditional transformation run fast, but produce less accurate reconstruction results. Dictionary learning-based methods generally output higher quality MR images, but suffer from slow reconstruction speed. The deep learning-based CSMR methods usually train a deep convolution network for learning the mapping from undersampled reconstruction images to follow-sampled reconstruction images. Although the reconstruction speed is fast for this method, it is difficult to define the agriculture of the network. However, to be gratified, the algorithm unrolling technique developed by Grieger and Lequin can combine the advantages of iterative algorithms and neural networks to build an efficient and interpretable iterative neural network. Inspired by this, our work makes the following contributions. First, we propose an improved learning IST for CSC based on the classical iterative shrinkage thresholding algorithm for solving CSC problems. Second, based on the improved learning ISTA, we propose ARCSCNet for CSMRI. The second part is the method proposed in this work. We first introduce the improved learning ISTA for CSC, in which we adopt image decomposition theory. We consider the high frequency and low frequency components of the image separately and use the CSC model to reconstruct the high frequency parts of the MR image. The specific iteration process is shown in the table on the left. We adopt a CSC model to obtain an accurate sparse coding, then decode the sparse coding to get a reconstructed signal, and add the reconstructed signal with the input signal to form the image domain residual structure. The following is our proposed ARCSCNet. The network agriculture is shown in the figure. It consists of a series of cascading subnetworks, each containing an ARCSC model and two data consistency layers. We represent the reconstructed MR image as X height and the inter-network model as F. Assuming that the proposed ARCSCNet has M subnetworks, the M subnetwork outputs the current prediction XM based on the output XM subtract 1 of the previous iteration and the input X0 of the network. The final reconstructed MR image can be described as equation 11. Next, we introduce four essential components of the network. We still focus on the agriculture of the ARCSCNet. Firstly, as shown in the orange part of the figure, The ARCSC model contains two submodels with the same structure, which process the real and imaginary parts of the input data. Secondly, as shown by the connection line at the top of the figure, we introduce a residual structure in ARCSC net so that each level of the subnetwork not only connects to the output of the previous subnetwork, but also receives the input under sampled MR image. Thirdly, ARCSC net relaxes the constraint restrictions on the CSC single dictionary, using multiple convolutional layers corresponding to different convolutional dictionaries, DD and DE, and completing the codec process in a manner that ACSC. Finally, ARCSC net uses the data consistency layer across multi-level subnetworks to implement constraints on key-space data. The third part will introduce our experiments and results, which are divided into ablation and comparative experiments. In the ablation experiment, we study the effects of the number of subnetworks and the number of iteration layers on the reconstruction performance respectively. As shown in the figure, both the PSNR and SSIM of the reconstructed image increase with the increase in the number of subnetworks. This figure shows the impact of the number of iteration layers on network performance. As the number of iterations increase, the PSNR value increase by approximately 0.5 dB as the number of iteration layers increase from 3 to 20. Below is a comparison of the results of a comparative experiment in which we compare the proposed ARCSC net with 5 advanced CSMRI methods, including these in the figure. It can be seen that at a sampling rate of 30%, ARCSC net obtains performance improvement at least 5.5 dB higher in PSNR than other methods. In addition, the images reconstructed by ARCSC net have higher SSIM and minor variance. Next, we give visualizations of each method. The first line is the reconstructed MR image, and the second is the corresponding error image. We can see that our proposed ARCSC net obtains the highest quality images with a minimum reconstructed error. In addition, we compare the runtime of each method in the table on the right. It can be observed that ARCSC net has better reconstruction performance without significantly increasing runtime. Finally, we summarize this work. Firstly, in this work, we propose an improved learning ISTA for CSC and expand it into a novel CSMRI iterative neural network called ARCSC net. Secondly, the proposed ARCSC net combines the advantages of traditional iterative algorithms and deep neural networks, which has good interpretability and excellent reconstruction performance. Finally, numerous experiments have shown that our proposed ARCSC net performs better in reconstruction speed, quantitative comparison, and visual quality than the state-of-the-art CSMRI methods. That's all I have to report. Thank you for watching.